My concern is with the ancient part of the hardware, which means PS is almost as old as I am. I'm not exactly young. I know that by the slot they built the SLC, the oldest part of the hardware given the most trouble. So I wonder if how well is that ancient part?
Well, I think the PS is 50 years old next year. Nevertheless, it's still going it's remarkably well. There has inevitably been some neglect during the construction time of the LHC. We didn't have a something to put into anything else. So there is a job to be done. I think that the PS is giving us the beam that we need to reach the design luminosity, but we have also a project for renovating. This will be over a number of years. The PS will still have to operate for a few years yet, but it's certainly a preoccupation of the rest of the infrastructure. If the PS is off, then the LHC is off.
But PS was working, because it's not like it was turned on when they turned it out, when they built 11, and then 10 years later they deactivated.
Oh no, the PS is working all the time. And the SPS, the superproton synchrotron. It's working at this moment. In fact, it's accelerating an LHC beam at this moment.
Well, at least you know what it's doing.
More questions? I don't see any more questions, so thank you again for this talk. And now we turn to the detectors, and the speaker is Jos Engelen.
That looks like it, yes. Yes, so I'll give you a brief report on the detectors around the LHC, on the conception of these detectors, and then at the end about the status. It is obvious that I won't be able to do justice to all of them, neither to all detail of even one of them, but I'll do my best to convey the situation as it is at the moment. So I'll tell you a little bit, in order to give this talk some basis about the design considerations, then about technical choices that have been made to really build these detectors, and finally I'll tell you about the status and first commissioning results. And the status basically is, as Lynn said, that these detectors are ready to take beam if it would be there tomorrow. They wouldn't be ready. If it will be there in 2 weeks' time, they will be ready. That is the situation. Now, for these detectors, obviously, we built on experience and knowledge we have gained at previous colliders. On the other hand, we have to realize that these detectors have to be radically different from earlier detectors for two reasons. One is the very high nominal luminosity of the LHC, and the other is the very high energy, obviously. So detectors have to be fast, faster than before, radiation harder than before, in particular also the electronics, the front-end electronics, and they have to be big, bigger than before. As far as the luminosity is concerned, you saw this formula come by. If you have paid attention, I have reproduced it here to indicate one other feature of the LHC that is very important for detector design, and that is that 40 million times a second you have beams crossing, so the timing of your device needs to be able to have a resolution to live in this environment. So that also put some a priori constraints on the intrinsic speed of the detector material, but also, of course, on the electronics design. So what is the spectrum of detectors we have at the LHC? We have two so-called general purpose 4-pi detectors, Atlas and CMS. They are the detectors to discover all the new physics that might be around. And they have also some capabilities for studying lead nucleus collisions, which is also a program at the LHC that I will not emphasize a lot in this talk. There is, however, one dedicated detector for lead physics for studying the core-gluon plasma phase diagram, which is ALICE. Then there is one dedicated detector for studying B mesons. It was realized early on that the LHC automatically also is a B factory with a huge cross-section for B quark production, and one detector is optimized with detector elements in the area where this process tends to send the B quarks, that is at low angles. Furthermore, precision measurement will be made of the total cross-section by one dedicated experiment, and there is a very small experiment that will profit from the energy of the LHC in a fixed target configuration equivalent to 10 to the 17th electron volts. Apparently that I use electron volts here because that's done in cosmic ray physics, I don't know why. But the LHCF experiment would be able to collect some data relevant for cosmic shower modeling. And then one experiment, but not right at the beginning, will of course search for magnetic monopoles. The experimental challenge is, as I said, the high interaction rate, which is about, in nominal conditions, about 1 billion events per second. That means that there will be more than 20 events at each crossing. And also that is, by the way, something new. That is an environment we haven't done experiments in yet. There will be a large particle multiplicity in addition. Because of this large average number of events, about 1,000 tracks will stream into the detectors every 25 nanoseconds. So you need highly granular detectors, many cells, many pixels if you want. And the high radiation levels, this is a hadron machine, require radiation hard, or if you're somewhat farther to the outside, radiation tolerant detectors and electronics. And a lot of this, by the way, Lynn talked about 14 years of construction time at the beginning. A lot of this technology was not available yet, had to be developed on the fly, so to speak. Now, the physics requirements that have to go into a detector design are numerous, and Oliver Buchmüller will tell you about the physics menu at the LHC, and all of that has gone into the detector design. But I have summarized one aspect here, that is the possible production and discovery of the Higgs, and depending on its mass, and on its mass, the production mechanism also depends somewhat. You need capability of detecting certain particles with a certain precision. So for a light Higgs boson, you might even want to find it in the gamma-gamma decay channel. That is not just masochistic, that it is also, but it is also one of the few possibilities one has for a light Higgs. And then the heavier it becomes, muon decay channels open up, and muon and jet decays combined. So this is one of the considerations that has gone into the detector design that I will come back to. Now, if you look at it, then you realize very soon that you need very good muon identification and momentum measurement, and you can quantify that even after the back of an envelope calculation, and set yourself the goal that your muon spectrometer should be able to measure muon momentum with a resolution of 10% at 1 TeV. Similar considerations, in particular referring to the low mass Higgs, lead to the requirement that you have very high electromagnetic energy resolution, and that you have very, very powerful tracking systems. And here the performance should be a factor of 10 better in terms of momentum resolution than we were used to at the previous big collider here at CERN lab. Then, this is already known since the early days of UA1 and UA2, it's an absolute necessity if you want to be sensitive to new physics and insensitive to QCD background. You need a very, very good missing energy resolution. That is to say, you need a detector without cracks and holes and leaks. And then I have absolutely no idea why this is between brackets here. I've written this transparency when I was younger, I think. The detector should be affordable. I considered that absolutely irrelevant when I was younger, but now I think, unfortunately, it's not irrelevant. The design considerations, then you go one step deeper, and momenta of particles you measure by deflecting them in a magnetic field. And so what you measure is the deviation from a straight line. That is a measure for the momentum. And you can here see that this deviation of a straight line is linear in the magnetic field. It is quadratic in the length of the track in the field, and it is inversely proportional to the momentum. In order to get this as big as possible, you need to get this as big as possible. So this formula already tells you why the detectors are big. What's important is the resolution. Now, you can determine from that formula the momentum resolution that you find in terms of the resolution of this measurement of this sagitta. Now, this sagitta measurement, that really depends on technology, on the resolution of your tracking devices. And silicon detectors now can manage to provide point measurements at 10 micron, drift chambers further down in the detector at somewhat higher energy. But also this factor F here is determined by state-of-the-art technology. Large magnets with high fields, not as high as the dipoles that Lynn referred to, but then the aperture of these magnets is larger, such that the stored energy is also huge. And there, state-of-the-art technology tells you that you can afford to have fields over sizable volumes of 1 to 4 Tesla. This upper limit is what CMS opted for. So a large L, as I said, is better than a high B, but the volume of the detector grows as the L cube, and at a certain point realism has to kick in, and realism kicks in between 1 and a few meters. Furthermore, there is one inconvenience of all these detectors. They need to be infinitely thin and infinitely light. And that is, of course, also something that one has to reconcile with realism at a certain point. Multiple scattering spoils your energy and momentum resolution. So it is mandatory to use very light and thin material. In the Alice detector, for example, the silicon detectors are 200 microns thick. If you look at them, they already break. So it is really pushed to the limit. Then there is calorimetry, where the energy resolution, because it's a statistical process that generates these showers, is inversely proportional to the root of the energy, and also there you have certain guiding rules to tell you what to do. This is one slide on electromagnetic calorimetry to illustrate what type of resolution, angular and energy you need in order to be sensitive to a light Higgs particle in this particular case. Similarly, for hadronic calorimetry, what you want is very good jet energy resolution, and you don't want cracks. The granularity, so the number of cells that you need to design, you usually start from one particle phase space, and one particle phase space is uniform in the azimuthal angle. It's also uniform in a quantity called rapidity, which is related to the polar angle, and this type of relationships then is a guideline for designing the granularity of the detector. So this all goes into the detector design. Muon spectrometers. Muons you usually measure at the outside of the detector, where all the other particles have been filtered away. So the only particles making it to the outside, so the calorimeters are muons usually, and there Atlas and CMS have chosen different solutions. Atlas has a very big, and I'll come back to it, standalone system for measuring muons. A muon, if the beam is perpendicular to me, a muon that is produced transversely in Atlas would make this pass. It would be bent like this in the central detector, and then it would bend that way in the outer detector. So this thing is totally independent, so to speak, of this. CMS had done it differently. They have a very high resolution tracker at the inside, and they will bend the muon inside like this, and then outside like that by the same amount for the return flux, which also has some advantages and disadvantages. This is the most conspicuous difference between Atlas and CMS. Then again, coming back to granularity, you have to design your tracker with a certain cell size, and there you use, of course, approximate Monte Carlo simulations of particle densities, and you know that at the inner part you will need very, very many channels to also have an occupancy, that is the number of channels hit in one event, that is low enough. Then you can afford silicon microstrips and other detectors to the outside. Now, these detector implementations have been published, in fact, last Friday. So last Friday, all the papers that will be referred to, that are the basis of the future physics papers, have been published. There was one separate publication for the LHC machine. So this has been published in open access, by the way. That is CERN policy. So you can consult all this for free. The machine and all the experiments that I mentioned will or have appeared in one volume of the Journal of Instrumentation. The Atlas detector, there is a drawing here. It is simply impossible to take a photo of it, even if it is existing. It is filling the underground cavern completely, and I don't think there is a point you can find where you can see the whole detector. So this, I will tell you in a little bit more detail. This muon spectrometer that I was referring to, here you see one of 8 very big coils. This is 25 meters, this is 5 meters, and this generates a field running air core, so there is, the air is the return, generates a field all around the detector here. And of course there are muon chambers installed for measuring the muons. This is the CMS detector where you see the various elements indicated. One important part, as I said, is that CMS has a very, very big central solenoid, a coil with a bore of 6 meters, 30 meters long, with a field of 4 Tesla that is filled with tracking devices. But also the calorimetry has been put inside the coil by CMS in order to have the particles disturbed as little as possible before they are measured. One other feature is that CMS really wanted a very high resolution electromagnetic calorimeter, and they developed a material for that called lead tungstenite, which on the one hand provides the resolution and on the other hand is sufficiently radiation resistant. This material that could be used by CMS didn't exist when CMS designed and decided to use it. They started with 1 cubic centimeter of the material to show that it could do what they wanted, realizing that I would need 10 to the 7th cubic centimeter in the end. Meanwhile, during the process, the price per cubic centimeter got up by $2 times 10 to the 7 is not negligible, as you can imagine. So this is a summary of detector implementations. I will not go through it, it's too boring now. It is important, though. One more remark about the magnets. Here it is indicated. These are also magnets with gigajoules of stored energy. So also the quench protection systems, the dump systems of these magnets need to be very, very reliable and tested, obviously. They are all unique objects, so they had to be designed specifically and then built specifically for these detectors. Atlas has 0.6 Tesla in here. It has 2 Tesla in the central solenoid, and CMS, as I said, has 4 Tesla. But the cable design for this magnet was, because of this high field, was something quite special. So what I will now do is I'll give you an overview of the status. So basically everything is there or almost there, and the very few commissioning results. I have used the most recent talks on it by the collaborations at the conference in Philadelphia recently. The Atlas talk by Martin Bosman and the CMS talk by Austin Ball. So I've made a selection. It is impossible to be complete, and I will see. I may have to skip some of the material on the fly now in the last 25 minutes. For Atlas, the inner detector is there. Now I draw your attention to this formula that you now recognize. That is the momentum resolution governed by these very simple considerations that I started with. And you can do the exercise in order to achieve a number as low as this one really requires state of the art. And this is then a residual term, which is typically due to multiple scattering, because you can't get away with zero material in your detector. So it consists of pixels, almost 100 million channels. So all of these channels are connected to an amplifier and to a readout channel. Then the strip detector, and Atlas has a gas filtered transition radiation tracker around that to sample points on tracks, very many with somewhat limited precision. But because of the transition radiation, it is also a device that will help to identify electrons. And all of this is now, in fact, installed in the cavern. The calorimetry features several technology from liquid argon to iron scintillator calorimetry. All this, well, the specifications are here. It doesn't make sense that I go through them in detail. All of this is now installed and working, in fact. Similarly, for the muon system, so this standalone muon system in this solenoidal, in this toroidal field out here consists of so-called monitor drift tubes. Those are drift detectors that measure individual points with a precision of 40 or 50 micron, in fact, which is absolutely spectacular. So now a little slideshow on the history of the construction and installation. Atlas is a very big detector, and it has been assembled piece by piece underground. So Atlas has been built, as they say, as a ship in a bottle. This is the bottle. Here it is still filled with officials, but they have been removed meanwhile. This is the shaft through which Atlas was installed, so that is the bottleneck here. And then today Atlas is built, as I will tell you. And this underground cavern is has these dimensions and is really very, very full. This is February 2004. The support structures for Atlas in the underground cavern that was delivered to the experiment, as you saw in 2003. The underground structures are being installed. The LHC, by the way, is not entirely horizontal. There is a little inclination also here in the cavern. And if your detector has a weight of 10,000 tons or so, a little inclination you better design into your support structure. So that has all been done. Then in July 2005, the installation of these magnets was progressing. Here you see that inserting it into the cavern through the shaft required the thing to be inclined. There's a lot of dedicated tooling in order to get it in, but so that has all gone very, very well. Then in 2004, the central magnet and the cryostat, also including the calorimeter, was lowered, and you see that step by step the cavern was filled. And now, if you are below Atlas, you have a look up here, and you see these muon chambers, for example, installed here, here, here. This is one of the later elements installed, the so-called small wheels. What you see here are the big wheels. These have been assembled underground piece by piece, and this picture was made when the muon detectors were completed. So in what I think is a relatively short time, the collaboration has really gone through a very, very successful installation and commissioning period. This was the moment that the beam pipe was closed. Now, this is not the beam pipe. These are shielding elements. The beam pipe is like that in there. You have to believe me that it is closed now. As far as the hardware readiness is concerned, all hardware is essentially ready and installed. Of course, few dead channels, and some refurbishment was necessary, but there was the time to do that. The beam pipe has now been baked out, and the magnet system has been tested. So that is a central solenoid, 8 barrel toroids, and 2 × 8 end cap toroids. They have all worked together. This is a placeholder. You need also trigger and data acquisition, very challenging at the LHC. I'll not go into that. I'll just tell you that at this moment, muons entering the cavern are being used to commission data acquisition, but also to look for properties of the detectors, resolutions, and all that. Now here you see the ship in the bottle, and what you see here is a reconstruction of the origin extrapolated to the surface of where the muons come from. And what you very nicely see is that most of these muons come through the shafts. The shafts didn't have the lid on here, and so this is sort of reassuring that what you measure is sort of what you expect. And the rate, because it is a huge detector, is still about 15 cosmic muons crossing the detector every second. I'll give you one example of what you can do with these cosmic muons. What you see here is a track through the monitored drift tubes. What you get is the time that the track goes by, is given by some scintillator measurement or so. And then you measure the time at which the signal, the ionization signal arrives at the wire in the center here, and from that you reconstruct where the particle went by. And this will need to be done with a design precision of 40 microns. At the moment it is 160 microns, but there are very, very many ways to improve this. So this is already a fantastic result. So for Atlas, the conclusion is that it is built and installed, that it is already the cavern in restricted access mode. That means that once beam will be declared, Atlas can be ready very soon. The commissioning activities are going on, and then the detector needs to be understood, of course, before physics can be done. Now, CMS is in a similar state of readiness at the moment, a little bit less advanced. There's still a little bit more work to be done in these last weeks. The conception of CMS is quite different. There, the detector is more compact. It has been constructed upstairs, not downstairs in the cavern, but in a modular fashion so that later it could be installed module by module. I'll show you a few pictures of that. In order to illustrate the planning that accompanies this project, it was known from the beginning that Atlas would need the bigger cavern. So Atlas got the cavern across the road where the conditions for making big excavations are better. CMS had to go to 0.5, the farthest away from here. But it was also known that the same company that was excavating the Atlas cavern would then, subsequently, not in parallel, excavate the CMS cavern. So CMS was building its detector at the same up at the surface at the same time as the cavern was excavated. Good planning. So that is why there are separate slides for surface and underground here. This is an illustration of when this started. At the surface, the muon return yoke or the magnet yoke is being installed, and the big vacuum tank in which the magnet coil is to be installed was there, and at the same time, deep underground, it looked like this. So this is not an experimental cavern yet. And then step by step, the situation improved, and then also the CMS cavern was ready fairly recently, in fact. CMS was built up completely on the surface. It was closed. It needs to be closed in order to be able to test the magnet. All the iron needs to be in place, and also that was done successfully. They profited from this by installing certain detectors partially only, but using cosmic rays, testing their detectors, but also testing the whole system from trigger through data acquisition to data analysis. This was the so-called Cosmic Challenge 2006 for CMS, and even there is a sort of a physics result coming out of that. What you see here is that that's a function of the muon momentum. The charge ratio mu plus over mu minus has been measured. It's indicated here. It was known already by L3 plus C, but still it's nice to illustrate that, that you start to know what you're doing with your detector. The heavy lowering, that is the lowering of CMS in its various parts, was done in a fairly short period. The heaviest piece is this one, that is the central part, that has a weight of 2,000 tons, and it went very well, and it was quite nice to witness that. So I'll not go through the details, just show you another one here. This is the magnet sticking out of the yoke here. This is how it looks in reality, and what you see here is that all kinds of cables need to bring either something into the detectors that are inside this magnet, or bring signals and signals out. The installation here was logistically incredibly complicated, but also there the collaboration was organized very well. I will then, nearly there for the detectors. I want to say something about the electromagnetic calorimeter of CMS. As I said, this calorimeter is used of a very special material, lead tungstenate. It was very difficult to procure all the lead tungstenate. In fact, there was only one company in Bogoroditsk in Russia that was delivering this, and I don't know whether it is of any practical value to you, but if you ever place a big contract, make sure that you place it with more than one company. This is the recommissioning of the tracker. It had been commissioned upstairs, but you see the cosmic muons that are reconstructed. It's really wonderful, and I don't exactly know what the residuals are here, but they are certainly completely consistent with the design, and also the signal to noise of these hits is very good. So the system integration, as I said, is going on. All detectors, and more of them, are working concurrently in cosmic rays, and I believe it is fair to say that also CMS is ready, is almost ready. It is very, very important for CMS to go through this in detail. We will not do that together here, but there is still some work to be done. But then at a certain point, alignment, calibration with beam halo events already, so even if one beam comes by and hits a residual gas molecule in the beam, that yields useful information. Then beam events, minimum bias events, and etc., etc. What the experiments will typically do is they will first rediscover, but at an energy where the measurements haven't been done yet, it will rediscover the standard model before, through that, understand efficiencies, calibrations, resolutions, and then, of course, look for new physics. For CMS, the conclusion then is that the construction of the experiment is almost completed, and that after the remaining steps, CMS will be closed. In fact, one side is being closed now as we speak. Then the magnetic field will be switched on again, but the magnet is cool at the moment, so that should not be a big complication. And soon after, CMS would be ready to accept beam. There are two more detectors that I will not go through with you, but we shouldn't forget. There is the Alice detector that is specially designed for heavy ion collisions. Now, for heavy ion collisions, the collision rate will be lower. The beams will be less intense. The luminosity will be lower. On the other hand, the multiplicity per collision will be fantastic. I don't know what the particle density is, several thousands per rapidity unit perhaps. So the tracking in Alice needs to be extremely powerful in 2-track resolution. And for that, inside a very big magnet with a somewhat lower field, but since BL squared counts, the size is very important, they have installed a time projection chamber around high precision silicon tracking, by the way, a time projection chamber, the biggest ever built, obviously, that should be capable of dealing with these huge multiplicities that are expected in lead collisions. And then there's another peculiarity that we have never done before, I think, is that this 4-pi detector is complemented with at one side with a muon arm, with a separate magnet, the dipole magnet here, in order to study psi, epsilon, etc. production in heavy ion collisions. So Alice features quite a number of technologies inside one detector, making the detector highly non-trivial. On the other hand, there had to be the choice, because it is an exploratory experiment at the same time, to be the choice of placing some detectors only in part of the solid angle, so not all of this is 4-pi. Then there is the LHCb spectrometer. So the LHCb spectrometer wants to trigger on B production at the LHC. Now, since the main production mechanism is gluon-gluon fusion, and since the two gluons hardly ever have the same momentum, the B pair will almost exclusively be produced in one hemisphere. That is why the LHCb spectrometer, for economic reasons, of course, is only a one-arm spectrometer with very high vertex performance to see the secondary vertices, with a very sophisticated trigger system, and with particle identification more than the others have, also to be able to do spectroscopy. This I'm not going to explain, but it is a placeholder to underline that the LHC computing grid is also a reality now. It was realized early on, but not very early on, that the amount of data produced at the LHC is going to be huge. And also here, this is a number that is much larger than what we have been dealing with before, certainly at LEP, where the production rate is modest, even if the luminosity was not. So in order to not only process these data, but also make them accessible to all the collaborators, a new way of computing has been developed in the computing grid that connects up computer centers, in fact, and also their storage, very large numbers of processes in a tiered architecture that has been completely tested and is ready to go. And it's not a luxury, and it is not to sort of allow others to play an important role in here. CERN itself can only afford to contribute at the level of 20% of the total requirement. So this is not a luxury but a necessity. And it has applications outside high energy physics also, as I'm sure you know. So this is my final transparency. It is at least qualitatively consistent with what Lynn showed, and there can never be a quantitative inconsistency because the timeline doesn't have a scale here. But at a certain point, very soon we will start, and then even by Christmas we hope to celebrate the 1 inverse picobar. And then if we would be here at the end of next year, that would be really fantastic. This type of luminosity really allows the experiments to cover, I don't know whether Oliver will come back to it, this will cover a large part, if not all, of the Higgs, the allowed Higgs region. That starts, as you know, at 114 GeV and goes all the way up to 1 TeV. So, either I have not been detailed enough, spoken too fast, or God knows what, but this is it. Thank you.
So thank you very much for this survey of the experiments. Are there questions?
One, otherwise I am depressed all evening. You don't want that.
So Bruce.
Can you say what are going to be the essential things that the experiments will need to change when you go to upgrade the luminance?